We're going to look in these notes at some more ideas about continuity, and then later on in the videos, we'll look at an important theorem called the intermediate value theorem. And so I'd like to start us off with an example that uses the idea of one-sided limits in order to obtain continuity for a piecewise function. So what we have here is f of x equals 3x cubed, and that's for x's that are less than or equal to 1. And so I'd like to go ahead and graph that. So when x is a 1, then our y value, 3 times 1 to the third, that would be a 3. When x is a 0, 3 times 0 to the third, that would give us 0. I'll do one more. When x is negative 1, so when our x is negative 1, then we take negative 1 to the third power, and that'll be negative 1, and then times 3, we'll get negative 3. So just thinking about what a cube graph looks like, it's not linear. You can kind of see that curve continuing. And then on the other part of the piecewise function, I have ax plus 5. And so when I start to graph that, I have to wonder what that a is, and that's exactly what you are asked to find. You want to find the constant a so that the function is continuous on the entire real number line. Well, it seems that this value of 1 is our point of separation, and we're going to need to find out what's going on there. So we can take the limit as x approaches 1 from the left. Now, when we have x approaching 1 from the left, we need to use the correct branch of this piecewise function. Well, from the left would be when x is less than or equal to 1. So that would be the 3x to the third portion of this function. In order for there to be continuity, the limit from the left must equal the limit from the right, among other things. So let's get this part done first. So then we'd have the limit as x approaches 1 from the right. And for that part of the limit, we need to use the branch of the piecewise function where x is greater than 1. And so that would be for ax plus 5. All right, so remember our approach to working with limits is to do the direct substitution. So we want to plug in the 1 on the left-hand side. So 3 times 1 to the third power would equal. And then on the right side, we want to plug in 1 again. Now remember, you're plugging it in for x. So it would be a times 1 plus 5. Well, now you have just a simple equation to work with. So 1 to the third is 1 times 3 is 3. A times 1 would give us a plus 5. We can subtract 5 from both sides and get negative 2 is equal to a. And so really you've satisfied what it says. You have found a. But let's go ahead and take a look at what happens here. So if a is negative 2, then this part of the piecewise function, ax plus 5, would actually be negative 2x plus 5. And whenever we're graphing piecewise functions, I always have students graph at the boundary, even if that boundary is not included. So we want to know what's happening at 1. Well, at 1, if we plug in 1 for the x, we get negative 2 times 1 plus 5, and we get that 3 value. So the 3 value was already colored in, and I know that I've now working at the starting point for this one is the ending point of the 3x to the third. I'm going to go ahead and graph a few more points. So when x is 2, we get negative 2 times 2 plus 5. And so that's going to be negative 4 plus 5, or 1. And you can also observe that this is linear. So if you wanted, you could go down 2 and write 1 again. And we have this portion of the graph. So we have continuity because the limit exists and the function value is defined at 1, and the limit equals the function value of 3. So when x is a 1, the limit is 3, and the function value is a 3. So the process will be to set the two sides of the limit equal to each other and solve for the missing variable. You might keep in mind that if you have two variables, to solve that type of problem, you'll probably need two equations. So think about that to kind of stretch this idea as you do your homework.